All right, let's get started. So we just talked about the nano lasers. So any questions about that? Oh, that's a very nice question. So basically, the question was, I mentioned this demonstration of nano laser with the electrically driven one. Okay. The question was, you are having metal surrounding the nanowires. This is a nanowire from which you should have emission, and there's metal surrounding all of it. So how is the light getting emitted? Where does the light come out from? Okay. So that's a very nice question. So the interesting thing here is you have to look very carefully into what is happening. So this is a very, very carefully engineered structure. Even though you're showing perfect metal here, this metal thickness is not going to be very large. So you make sure that the metal is thin enough on the top so that it can actually transmit light. If you have something like 100 nanometer light, it will basically reflect everything. You cannot transmit light. You cannot have outcoupling of light. So you have to make sure that the thickness of the metal is optimized so that you have good reflection, so that the cavity is good, but then still it should emit out. All right. And in addition to that, if you notice carefully, there's a lot of different layers of semiconductors that are present. You see 10 power 18 doping, 10 power 19 doping, and various N and P types and so on. So why do we need such a careful design? It turns out that the electrically driven nanolasers is a very challenging aspect to demonstrate that, because we know from our basic semiconductor devices that if you have a contact between a metal and a semiconductor, there's a Schottky junction. So a Schottky junction means that there is a resistance there, and it actually lowers the efficiency of your laser. So if you want to have a good working laser, we need to make sure that there are the Schottky barriers which are avoided, or at least minimize the junction width, Schottky barrier width, so that tunneling happens and we can overcome that. So in this case, that's why whenever you contact with metal, they try to have large doping so that the barrier is very, very small and narrow, and you can actually overcome that. And also the entire structure has to be very, very carefully designed so that you minimize basically the resistance for both electrons and holes. So a lot of careful design is done to do this. And in fact, if you see this, the bottom contact, so this is my nanowire. So the lasing should happen from this red region, and everything else is basically the P-type contact and N-type contact. So you'll see that you'll have electrons from the top here, and the bottom is actually from this side, the side. You actually etch out what is called as a mesa, and then you make a contact with the bottom layer, and from that you inject holes into the structure. Okay. And from the top you have the electrons which are injected. So it's a beautiful piece of engineering that actually gives you this. So yeah, so that's a very nice question. So that you are able to relate to the earlier concepts of electromagnetic wave transmission through metals. So that's why nanophotonics is that beautiful interdisciplinary field wherein you need expertise in optics and semiconductors and electromagnetism, and even quantum mechanics you'll see down the line. All right. So yeah, thank you for the question. Yes. Anything else? All right. If there's no other question, let's move forward. So now in the next half an hour or so, what I'll do is actually give you a flavor of the work that we are doing. So I'm personally involved. So just indulge my vanity here. So I'll show you a little bit of our work. So far, we have given a historical perspective looking at what's happening world over. But now I'll just focus on just our work for the next half an hour or so. So this is a topic that's very close to my heart. That's why I work in this, and also we want to understand it in a very fundamental way. So we talked about nanoscale lasing, right? And we said there are this metal nanostructure, metal dielectric combination that is required to actually miniaturize light. Now, in addition, in the last 10 years, or rather 8 to 10 years, we have a lot of work on Me resonances in nanoparticles, and I was involved in this work personally. So here we have one particular structure wherein we fabricated gallium arsenide nanoantennas. These are gallium arsenide nanoantennas. Diameter of these antennas is about 200 nanometers, and the height probably is around 250 nanometers. When you have this array of antennas, so in the previous lecture, I emphasized the individual nanolasers, but I also said towards the end that you can have these arrays, and that can actually create lasing in nanoparticle arrays. So this is one such example like that. So when you have this array of nano antennas, it turns out that they have some interesting properties. Now, we have already understood how a dipole behaves. So if you have a dipole that is oriented out of the plane, we know that the electromagnetic energy is actually radiated in the donut shape around it. Now, what happens if you put an array of such dipoles? In principle, each of them should actually not emit in the vertical direction. So in the vertical direction, there should not be any emission, because just the dipole cannot exhibit emission in that direction, right? And then it should emit in the other directions. But now if I create an array in such a way that I cancel the emission from each individual antenna, it destructively interferes, or maybe you form an array and it has a diffraction order at a particular angle, and you see that in this, let's say this is my diffraction order for this particular periodicity, then each of this antenna will emit into that particular direction, and that is a preferred, you can have directional emission from that. Okay. Now we can also try to create a scenario wherein you make it sub-diffractive array. That means you will not have diffraction. You can cancel out the diffraction. And if you have such a scenario, the dipole itself cannot emit in this particular direction, and you made it sub-diffractive, so it cannot emit in any other direction. So essentially, the electromagnetic energy has to be bound inside the nanoparticles. Okay. And this basically is the origin of a concept which is known as bound state in continuum, and there's a lot of excitement around this. So what we did was we took these structures, we patterned them in this form, and then we pumped it optically. Okay. When we pump it optically, what you see is the similar trend that you have seen in the past. So at low optical pumps, so that this is pump fluence, which is 7 microjoules per centimeter square, and then you see that there is broad emission. But as you increase the pump energy, you see that there is this transition from a broad amplified spontaneous emission into this lasing line that comes about. And if you look at the quality factor of this line, it turns out that it's very, very high. The Q factor is on the order of 2700. And if you look at how the output intensity varies as a function of input, so in the lasing community, we call it a LI line, or in this case LL, basically light input and light is output. So basically, if you look at that, and you plot it in the logarithmic scale, you see the characteristic S curve in this fashion. So this is basically a signature that the lasing is actually occurring here. So lasing threshold occurs around 10 microjoules per centimeter square. And once below the lasing threshold, the width of the full width half maximum of the emission is very large. But once you cross a threshold, you see that the full width half maximum falls down into nearly only 1 nanometer or so. So this is a characteristic signature of lasing, and we have seen that. And we also can see that this sort of emission that happens, it can be tuned. If you change the periodicity of the nanostructures, you can actually get emission at different angles and different wavelengths and so on. So this is one of the keys. And I think mentioned in passing that this line width, narrow line width, is one of the signatures. A more accepted signature of lasing nowadays is actually to measure what is known as G2 function, the second order correlation function G2. And if you look at what a G2 of 0, if you get G2 of 0 equal to 1, I'll actually discuss more about the second order correlation function in the quantum optics part of it. So maybe in week 9 or 10, I'll discuss more about this. But essentially, if you show that you can measure the second order correlation function for the emitted intensity, and if you show that G2 of 0 is 1, that's the signature of lasing. And that's what we have seen here, at G2 of 0 at each pulse, along with, you see that there is this G2 of 0 which is constant. Okay, and it's a signature of lasing. So now what you see is you have lasing from this structure, but there are several drawbacks. One of the first drawbacks is this demonstration was actually done at low temperature. Okay, this was done at liquid nitrogen cooling to 77 Kelvin, and the threshold in this case is quite large. 10 microjoules per centimeter square is a large amount of energy. This was actually pumped with a femtosecond laser, so you're depositing a lot of energy into the structure to actually make it lace. Why was the threshold high? It turns out that the losses in the cavity or the gain is not sufficient. That's why the threshold was high. You have to pump it very high levels. And of course, we are actually done only optical pumping, and that is not really that, it is good for a demonstration or exploration of ideas. But if you want to actually have practical devices, you need to have them electrically pumped. And that is still, we showed you one example from 2007, and we need to do something similar to that. So that's a lot of challenging work that needs to be carried out. All right. So, but what the question is, the threshold is high because the gain is low. Can we do something about that? Okay. This was an interesting problem that I started thinking about sometime, some years back. So the idea is, when we did this particular demonstration, we naively chose the gallium arsenide nanoantennas to be intrinsic nanoantennas, intrinsic type. So there was no doping into that. And that was most probably the worst kind of choice that I could have made. We didn't know about it while we did that, so we struggled and we demonstrated. But it turns out that the optical gain from an intrinsic gallium arsenide structure is very small. It's not large. Then there's a very simple reason for that. So I showed this particular diagram in the past, and I said that if you have this sort of a scenario wherein a conduction band and valence band are there and you excite it, and I said that there is this quasi-Fermi levels that are created. But if you notice closely, the quasi-Fermi level for the electrons is into the conduction band, whereas the quasi-Fermi levels for holes is not really into the conduction band, it's still in the band gap. There is a reason for that. The reason is, if you look at the effective masses, I can talk of effective mass for electrons and an effective mass for holes. Okay. And the effective mass, we know from our semiconductor courses, the effective mass is basically inversely proportional to the curvature, right? So if you see that is inversely proportional to curvature of the band. So you see the electron, the conduction band is very steep, so its curvature is large, and so it has a small effective mass, whereas for the holes, the curvature is small, so the effective mass is large. So if you have effective masses this way, the density of states, I know it's a little bit of an extra information, but the density of states is basically proportional to the effective mass, and so there's a large density of states that is available in the conduction band, because of which the Fermi level moves slowly towards the conduction band in the case of holes, whereas for the electrons, the Fermi level moves quite deep because there's a less number of states available, density of states available. So they will get filled up, and quickly you'll start seeing the higher energies get filled up, and because of that, the quasi-Fermi level essentially moves into the conduction band, whereas that doesn't happen in the case of a valence band. Okay. So once we understood that, we started looking for ways by which we can actually improve the gain. And the reason the gain is not optimal is there is this mismatch in the way the quasi-Fermi level moves into the valence and the conduction bands. And so what can we do to address that? Well, we did a lot of study. It's done already previously in the semiconductor community, but we sort of had a relook at it. And it looks like if you actually have p-type doping, that's beneficial for lasing. Because if you have a p-type doped semiconductor, the Fermi level, the equilibrium Fermi level will be somewhere here close to the valence band. And then when you pump it, the quasi-Fermi level moves slowly towards the valence band, but still already it can go deeper now compared to the previous case where it was intrinsic doping. And the quasi-Fermi level for electrons moves, in the regular fashion. So with the p-type doped semiconductor, we can get better gain. And if you also have strain in the semiconductor, that will also improve the gain. So these are two particular pieces of analysis we have done and we figured out, and we think that will actually improve the gain, and so we can actually achieve lasing with lower thresholds. But when we look at nano antennas, there is another piece of problem. That is, we are actually, when we talk about the band structure and everything, or we talked about it, we said that the bands are all for infinite lattices, perfect lattices. But the moment you pattern a semiconductor into something like a nano antenna, like a 200 nanometer diameter antenna, it turns out that on the surface there are states which are created, surface states which are created, which in the bands, if you think of a conduction band and the valence band in this fashion here, conduction and valence bands, in addition to these, there are some states which are created in the forbidden region or forbidden band gap region. Within the band gap, there are these states which are created, which will actually help the electrons to recombine with the holes in a much more efficient manner. So because of that, it turns out that if you have these surface states that are there, there's an electron hole recombination that happens non-radiatively, and the lasing threshold is very high. Okay, so it turns out that gallium arsenide again is a worst material for surface recombination. It has a very large surface recombination velocity, and so we investigated what happens if you have surface recombination with various surface recombination velocities. How does the gain behave? So we did a lot of analysis in this direction, and we computed. I mean, it might. There's a lot of detailed knowledge that is required, and one of my students did that. The first student did this. So essentially, we combined the DFT calculations for band structure and also modeling the carrier dynamics in COMSOL. We combined all of that and evaluated how the gain behaves. So in the previous case here, I showed you a nice picture like this, how the gain changes, but in reality, the gain would actually be something like this. And as you increase the surface recombination velocity, it turns out that the gain reduces, and you see that there is this, it's tending close to the loss. Okay. And similarly, in the case of, if you have strain, the situation is slightly better. So in this case, the gain is low, but positive at low surface recombination. At high surface recombination, it's effectively loss. But if I have strain here, the second picture is the strain, and we see that the gain is reasonably larger over a broad range of wavelengths. Okay. And we also try to investigate what happens, what are the fundamental limits, what is the gain that we can expect out of nanostructures. So as you shrink the size of the nanostructure, we see that the gain reduces, and that is something that we can expect anyway. All right. So this is an interesting study that we did. So, and the overall conclusion is that if you have p-doping and strain and surface passivation, or either or all of them, you can actually improve the optical gain, and we can actually have lower threshold. But in addition, we also need to improve the cavities. The cavities that we have designed so far are the classical cavities. So initially we had the edge emitting, then we evolved towards the vertical surface pixels, surface emitting lasers, and then we moved towards the microdisc and the nanodisc and so on. But is there anything else we can do in terms of designing cavities? Okay, I'll talk about that in the next lecture, and with that I'll close the discussion for this week. So just to summarize, what I talked about was, we initially talked about the lasing which occurs in these antennas or other nanostructures, and we talked about, I introduced a new type of antenna that just has these various nanodiscs, which are nanopillars, which are arranged in a periodic lattice. And I said that if you have such a lattice, you can actually have lasing, which appears as a very sharp peak. And now that lasing, while it is nice and interesting in terms of physics, it has limitations because you essentially have to work at low temperature, and it has a high threshold, and we need to optically pump. So all of these are not really good for us. So we started looking at how to lower the threshold, and one of the directions for that is actually to introduce p-doping, strain, or surface passivation, right? So some of these are known in the community, for lasing community, for a while, but I think in the nanophotonics community, I think this information is not that widely understood. So I think we took a detailed look at it, and then the details are all there in the papers. If you're interested, you can look at it and we can talk. But I just wanted to give you a flavor of what is happening currently. All right. So with that, any questions? I'll ask you one question. So I said gallium arsenide has a high surface recombination velocity. So it's not good. So what can we do about it? Passivation is one thing. What else can we do? Yes. The answer is you can change the material. So if you have gallium arsenide, there's nothing much you can do about the material property. So it has a surface recombination velocity of about 10 power 5 centimeters per second. But if you choose things like indium phosphide or gallium indium phosphide and things like that, so the surface recombination velocity is much lower. So that is probably a better way of actually demonstrating lasing instead of gallium arsenide. Okay, the question was, why is the surface recombination given in terms of velocity? Okay. Okay. Generally the recombination is recombination lifetimes. Why are you talking about velocity here? Well, the idea here is that if you make a nanostructure, I said that there are these surface states. I think I tried to, I didn't really talk about the details, but essentially what happens is this number of surface states are going to depend on the surface to volume ratio. So if you have a big structure, the surface is not really that significant. You don't have to worry. But the moment you come down to nanoscale, the overall area, for example, you take a sphere. The surface area is 4 pi r square. The volume is 4 by 3 pi r cube, right? Now, if you take the surface to volume ratio, you will see that as you go to smaller dimensions, the surface to volume ratio increases. That means you have more surface effects. And now on the surface, we have these states which are available, and they're going to cause recombination. So now what is going to happen is, if you pump it, that's something that, we have done this. So we pump it. In a typical structure, we'll say that, oh, we created electron hole pairs and we have gain. But the moment you consider a nanostructure, it's not true anymore, because the carriers at the surface are getting recombined through the state, and then new carriers are coming towards the surface. So there is this constant flux of carriers from the center of the nanoparticle towards the edge. So there is a speed with which this, the velocity with which these carriers move, and I can quantify surface recombination using this. So, if you look at the semiconductor physics, you might remember that the drift current is given by NeV, the charge times the number of electrons times the velocity, drift velocity in that case. Now we sort of we create basically the surface recombination current I could define in a way that the charge times the number of carriers times the surface recombination velocity. So if you have a large surface recombination velocity, that means we are actually having a lot of carriers which are recombining. So it's a metric essentially, and it turns out that the speed with which the carriers move towards the surface is an important parameter. So surface recombination velocity. Yeah, it's a little bit more. There are a lot of interesting semiconductor physics there. Yeah, if you're working on that, we can talk more. All right. So yeah, any other questions? Oh, the question was, what is this strain, and can you talk about it? Well, yeah, again, strain, I didn't really talk much. So I said that you have this effective mass difference, and that is actually causing the gain to be lower. Okay, you might not understand all the details, but it's okay to just know about it, know the areas which are important. Now, if I apply strain, essentially I'm changing the curvature of the bands, and that is something that was already done in the CMOS community. When they introduced, let's say when they went from 90 nanometer, 65 nanometer technology in the CMOS, strain was introduced. So essentially you create strain in the channel region so that the mobility of the transistor improves. How does the mobility improve? Strain actually changes the effective mass, and so mobility improves. Mobility is simply the effective mass times the, E tau by m, right? The scattering time by m. M is effective mass reduces, mobility improves. So that was done. So essentially when you apply strain, essentially you're stretching the lattice, and it turns out that the curvature of the bands changes. And when you have such a scenario, you have better gain. Okay. So for those of you online, I think if you're looking at it, it might be a bit of information overload. Excuse me for that, but we are talking about a frontier area of research, and I don't know how I can I've tried to simplify it as much as I can, but I think there are some aspects of it which are quite involved, and I think it's okay if you don't understand all of it. I'm trying to give you a flavor of the research rather than make you an expert in this. So over time, I think you accumulate, an individual accumulates a lot of knowledge, and if for somebody who is just getting exposed to that, it will seem very, very complex. But it's not that complex. With systematic effort, I think you can understand all of this. And if you want to work in the forefront, I think you have to be exposed to this. So, if you're starting out in the first grade or second grade, even reading a small sentence would have been difficult. But now it's very natural. It's something similar that happens with me. I have been working in this field for about 10 years now, 10, 12 years. So for me, some things are simple, but if you're just starting out, it might be complex. But I would say that, don't get perturbed by that. It's okay to not understand everything in all the detail. When you're actually looking at new technologies, it's important to get an overall big picture right. Once you understand that, there are always details that you can learn over time. The important thing is to actually be exposed to a wide variety of areas and try to understand them at a high level first. Okay? And then you can go deeper and deeper if you choose to focus on that. But it's important to understand the broader concepts. All right? Okay, then, there are many things, even, very interesting things. We talked about the strain, right? The bands will change. The band curvature will change. What is an analog for strain in photonic crystals? In photonic crystals, because we came up with this idea of photonic crystals, and then there is bands and all formed, and then how does the curvature change? What is the analog of that in photonic crystals? Anyway, so yeah, just try to relate ideas from various areas. Okay, so yeah, so please excuse this a small detour, but yeah, okay, I'll see you in the next lecture. Thank you so much for your attention.